And on to the third and final problem we're going to do in 3.10, the cops and robbers problem. All right, guys, let's see what's going on here. So a robber is heading east, away from an intersection, traveling at a speed of 60 miles per hour. We see and we think about and we hear miles per hour so often that we forget sometimes that that P right there means per. Miles per hour is actually a rate, everybody. Miles divided by hours. And that might tell you something. That's a derivative. That's a rate of change. So a robber is heading east away from an intersection at 60 miles an hour. A cop is chasing that robber, heading south towards the intersection at 80 miles an hour. All right, I'm going to stop right there. I'm going to try to draw what's going on. All right, guys, we have ourselves an intersection, okay, and you heard the directions north and south and east and west, or two of those four anyway, so I think it's fair to assume that we're dealing with one east-west road and then one north-south road that looks something like this. And where are our principal characters? A robber is heading east away from an intersection. That must mean that the robber's position is probably over here somewhere, heading east away from the intersection. So that right there is where our robber is located. Now, let me go ahead and stop right here. The distance between the intersection and the robber. Let's build on the discussion we just had about the hot air balloon problem a minute ago. Is that quantity right there between the intersection and the robber's car changing? Or is it constant? Well, it's a pretty bad getaway chase problem right here if the robber is standing still. That's a variable quantity, so we're going to go ahead and put an R right there. Then, what else do we know? The cop is chasing this robber, and the cop is heading south toward the intersection. Heading south toward the intersection. That must mean that the cop is currently located north of the intersection right here, but is heading down in this direction towards that. Now, the distance from the cop to the intersection, is it constant or is it variable? That's changing as well because the cop is chasing after the robber, so we're going to have to put a C right there. Okay, so I don't think I can move 2 points at once, but what's happening? Cop is moving towards the intersection while robber is moving, that was weird, robber is moving away from it. And eventually, in theory, the cop will turn the corner and they'll both be heading the same direction, but we're not there just yet. All right, so let's get back to where we were, and this setup looked a little something like that. Now that I think about it, I don't think I need that second dot right there, so let me get that guy out of the way. That's a bystander. All right, so what's happening next, guys? The question now is, how quickly is the absolute distance between the cars changing when the robber is 0.6 miles from the intersection and the cop is 0.8 miles from it? Let's go back to the question at the beginning. That's wordy. How quickly is the absolute distance between the cars changing? Okay, when we talk about absolute distance between two things, that is the direct straight line measurement, everybody, between 2 points. So that red segment that I just drew, that's going to represent the absolute distance between the cop's car and the robber's car. Not as opposed to what's called, I learned in a college geometry class, like a taxi cab distance, which would be the sum of that distance plus this distance right here. When we say absolute distance, we mean as the crow flies. So I think you guys can already see from this diagram what's happening. Because we're talking north, south, east, and west, we can assume perpendicularity in our diagram here. And I think this means I've drawn more than I probably needed to, so let me get rid of some of this stuff right here. This is kind of what's happening in this case. Okay, so we need to think about in this problem what derivative we know and what derivative we want to know. So we're looking for rates of change, everybody. And as I go back and I look for rates, for example, in the first problem, that rate was 15 cubic feet per minute. In the second problem, the balloon was rising at a rate of 2 feet per second. You're looking for the word per, and we've got that here, and we've got that here. The robber is heading east away from the intersection at a rate of 60 miles per hour. That means, guys, that this robber's distance is increasing at 60 miles per hour. So that is the derivative there of R. with respect to t. So the derivative of r, which is the distance from the robber to the intersection with respect to t, is going to be 60, and that's going to be miles per hour. And if you want to write mph, that's great. And if you want to write it that way as a ratio, miles over hours, that works too. But the interesting thing about this problem, I think you see it already, is we also know, guys, that the derivative of the cop's distance to the intersection with respect to time, that one is going to be 80 miles per hour. Okay, because what's happening right here? The cop is moving too at that rate there of 80 miles per hour. So there's actually two derivatives in this problem that we know. And the derivative that we want to know is what's the rate at which the absolute distance between the cop and the robber is changing. So since we in our diagram labeled that distance d, and yeah, I did that on purpose, we want the derivative of distance, d, with respect to time. But we want this at a specific moment, at the moment when the robber is 0.6 miles from the intersection. So that's r, 0.6 miles. And the moment when the cop's distance is 0.8 miles. So as I think you guys can see, this problem is a little bit more complex than the first two that we've done because there are two derivatives now that we know and two values, everybody, that need to factor into our eventual equation we get after we differentiate. But let's not freak out, everybody. This is actually kind of a good thing. If we go all the way back to problem number 1, we had an issue right here with the fact that there were actually 1, 2, 3 variables in that equation. And if we had differentiated that equation at that moment, we would have a dv dt, a dr dt, and a dh dt. We didn't know dr dt, so that was a problem. But in this equation, or what we're going to end up with here in a second, we actually know two derivatives, and we're looking for a third. That means that it's okay if I come up with an equation right here that actually has 3 variables in it, because I think I know how to deal with it when it comes down to that moment. So let me slide all of this over just a little bit, everybody. Okay, that'll work, and let's get started. The first thing we have to think about before we can relate the derivatives of r and c and d, we need to think about an equation that relates just these 3 variable quantities. And I think you guys probably saw it already. We're not talking angles in this problem. It's a right triangle, and we have a representation for all 3 sides within this triangle. So what ties all 3 sides of a right triangle together? The Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. So r squared plus c squared is going to equal d squared. And if I only knew one derivative and I was trying to find a second, we'd have to find a way to relate these quantities together. But lucky for us, we're good with all 3 of them. We know the derivatives of dr dt and dc dt, and we're looking for dd dt. So here we go, guys. The derivative of r squared is going to give us a 2r times the derivative of r with respect to time. Gotcha. Plus, the derivative of c squared is going to be a 2c multiplied by the derivative of c with respect to t. And that equals now, I think you get it, the right side is going to be 2d multiplied by dd dt. Okay, and what gets really interesting here is that we have 1, 2, 3, 4, 5, 6 variable quantities. The one that we're looking for is dd dt. That means that we better know the values, the time-specific or constant values for the other 5 things. And let me say again, it's okay now to use time-specific values because we have differentiated. So, at the moment in question, they tell us that the value of r, the distance here, let me switch to green here, the distance from the intersection to the robber, they tell us that at that moment, that's 0.6 miles. So this is a 2 times 0.6. And they've also told us that dr dt is that 60 mile per hour rate that goes right there. So that's dr dt. Plus, let's keep going now, 2 times, all right, where are we now? C, the distance from the cop to the intersection right here at the moment in question is 0.8 miles. And once more, it's okay to now use a time-specific value like 0.8 because we've already differentiated. And the dc dt, the rate at which the cop's distance is changing, that is going to be 80 miles per hour. And I think right now, guys, I got to get rid of some of this junk that I drew over here because it's just, there's not room for it. Okay, we'll do that. Okay, so that's the left side. It equals 2 times ruh-roh. We got to figure out what d is. And I'm comfortable not knowing dt because that's what we're trying to solve for in this problem. But we better figure out this value of d at this moment in question. So how are we going to do that? We could go back to this equation right here, the Pythagorean theorem, and use 0.6 for r, 0.8 for c, and we could figure out d. Or I'm wondering if you guys just noticed that I did you a favor right here. 0.6, 0.8, d is equal to 1.0. This is a Pythagorean triple, everybody. It's a 3, 4, 5 that's really being divided by 5. 3, 4, 5 gets doubled to make 6, 8, 10, and then you divide all those sides by 10, and that's where we are here with the 0.6 and the 0.8 and the 1.0. You're welcome, world. So I'll go ahead and put a 1.0 right there. That is the actual distance between the cop's car and the robber's car at the moment in question. But the question we're trying to answer is that distance right there growing or is it shrinking, and at what rate? So here is where we're at right now. Let's see what we can't do to clean all this up, everybody. Oh, I don't know. 0.6 times 60. That's going to be 36 times 2 is going to give us a 72. Plus 0.8 times 80, that is going to be 64. 64 times 2 is 128. And all of that equals a 2 times a dd dt. All right, so where are we now? The 72 gets added to the 128. Oh, that's convenient. And that works out to be 200 exactly. And then when you divide that by the 2 that we have on this side, I think we've got our answer now of dd dt is equal to, we just said 200 divided by 2, looks like it's going to be 100. If we think about the rate at which a distance changes over time, we were measuring here in miles divided by hours. Now, everybody, that looks like our answer, but I want to think for a second and interpret what exactly that means. D is the distance between the cop's car and the robber's car. So imagine, silly as this sounds, there's a giant rubber band stretched between these two cars while they're driving. We're now saying that the distance, or the rate at which that rubber band is changing is 100 miles per hour. That derivative is positive, which means that this d distance is actually growing and expanding at a pretty darn fast rate of 100 miles per hour, even though it seems like the cop is actually closing in on the robber, and you might expect that that distance should be shrinking. Now, everybody, there's a mistake that we've made in this problem. I made it on purpose, and we're going to go back and fix it, but I wanted you guys to see what it looked like, and I also want you to take this little moment of reflection here at the end to think about what your answer means and what it's suggesting and whether or not it's realistic. And I didn't feel like this one was realistic. So I wonder if anybody caught the mistake that I made a while ago. It was a long time ago. The mistake, everybody, dealt with what I drew in red in this diagram. The robber's distance, the robber's rate, I should say, 60 miles per hour, represents the rate of change of the distance between the robber's car and the intersection. The question I have for you guys is that distance right here growing or shrinking as time goes on? The answer to that, it's growing. It's increasing. And a function that is increasing should have a positive derivative. So I feel pretty darn good about that positive 60 right there. But now, as we start talking about the cop, we said this a while ago, the cop is actually moving towards the intersection. meaning that the cop's distance, which at this moment was 0.8 miles, is shrinking. The cop is getting closer to the intersection, so C is decreasing, which means the derivative of C would have to be negative, indicating then, everybody, oops, sorry about that, indicating that that quantity is decreasing. So the mistake that we made was that we should have put a negative right there on the 80 because the cop's distance is decreasing. So what does that change for us, everybody? That means that this beautiful plus right here really should have been a minus. Shoot. So now that changes quite a bit, actually. Let's get rid of that. The 72 minus the 128, I do believe, is going to give us a negative 56. And when we divide that negative 56 by 2, I think we're going to get a negative 28 miles per hour. And what that negative answer tells us is that at the moment in question, this distance between the cop and the robber is actually decreasing. And that kind of makes some sense since the cop is moving at a faster speed, not velocity, everybody, but speed, than the robber was. So I think it makes sense that that distance is shrinking and that our derivative then is actually negative. So that's a really common mistake that people make in velocity or problems like this. So I wanted you guys to see it made and hopefully then understand why that 80 needed to be negative and how that impacted our overall answer. All right, guys, that is a wrap not only on section 3.10, but on all of the notes that we need to do in the first semester. So congratulations, pat yourself on the back, go have some ice cream and do something to make yourself feel good, and we'll see you guys back here for the second semester. Good luck, everybody.